Hello. In a previous video, I described de Broglie's hypothesis, which says that an electron has both particle properties and wave-like behaviors. Heisenberg is a continuation of this thought, and we will look at his uncertainty principle, plus we will calculate uncertainties, something that some professors do, but most professors don't. And these uncertainties are what? Uncertainties in the position of an electron and the speed of the electron. Okay, that de Broglie hypothesis discussion was in video 03H20, but in this video, let us discuss Heisenberg uncertainty principle. And simply, or maybe not so simply, he tackles this conundrum where can you really understand or know for certain the position of an electron and the speed of an electron at the same time? Just give me a second or two. Okay. He says that it's impossible to know simultaneously the momentum, and recall that momentum is the product of mass times velocity. And position, momentum and position with certainty. As you know, one with certainty, the other one decreases in certainty. And there's actually a mathematical equation for this. That mathematical equation is, now I'm not 100% sure, but we'll just call this delta x, but it's not a changed x. I'll tell in just a bit what this really means. Here's your momentum, greater than h over 4 pi. The uncertainties, the product of the uncertainties is actually greater than this number right here. I know that sounds a little bit odd. We are going to do some calculations and apply some numbers to these kind of abstract concepts. But let me give you at least some introduction to what these terms are. So this is uncertainty in position. And let me just double check. This is important. The units are going to be in meters. Okay, it's almost like an error, plus or minus. This is, again, momentum, uncertainty, and technically we are going to focus on the uncertainty in speed, because this term, and maybe I'll rewrite this, equals the mass times, again, I think we're going to consider delta as uncertainty in the speed. Okay. Let me rewrite this, actually. The equation that we'll be using is this m okay, and let me square it off. All right, so how are we supposed to think about this equation from Heisenberg? First of all, these two uncertainties are inversely proportional. And if the mass is larger, like a baseball, then yes, you can know pretty certain what the speed of the baseball is and the location of the baseball. And let me write that down. What Heisenberg said is that then both the uncertainties are insignificant. So what that means is you can pretty certain locate a baseball and know its speed at the same time. You can know speed and location. And actually, when we talked about de Broglie's wavelength equation, we saw that the wavelength of an object, like a bullet or a baseball, is minuscule. I think the number was 10 to the minus 30, 10 to the minus 35 meters. So that wavelength is not even observable. And if that is true, then you could just use classical mechanics. It falls apart when the mass is very tiny and the speed is very fast. So let me just finish my thought. Here you can use classical mechanics to pinpoint, um, say, speed and position. And then finally, and then we could probably get on to some calculations. This certainty, let's say, falls apart with very tiny objects with fast speed. Okay, let me find some paper. Again, if you think about an ocean wave, or first think about an electron that has this dual personality, well, how do you locate a single electron that acts like a particle when it also acts like a wave? Because a wave, like an ocean wave, is spread out. And I know that's not a great analogy, but it does point to the idea that there's some difficulties in understanding both the position of an electron and its speed when you have this wave-like property. This is the example I want to try. We have an electron, and the speed we'll put as 5.0 times 10 to the 6 meters per second. But we also have an uncertainty for that speed. And we're going to first format it as a percentage, plus or minus 1%. Let me give you the mass, because that was part of Heisenberg's uncertainty principle equation. Mass equals 9.11 times 10 to the minus 31, and we are using, again, kilograms, just like we did for the de Broglie wavelength. Diameter is about 1 angstrom. 1 angstrom is 10 to the minus 10 meters. So here's a question, and it's a kind of a goofy question. What is delta x? Again, this is going to be in meters, and we said that in the previous page. And really, what is the uncertainty principle? or let me just double check. What is the uncertainty in position? Not only is it a odd question, the answer also is a little bit odd in terms of its format, but we'll work this out together. Okay, the first idea is that, well, let's make sure we know the equation first. Planck's constant over 4 pi. So this is unwavering, or this is constant, all right? And remember that the uncertainty in position and speed are inversely proportional. Okay. We do know, or we could get at the uncertainty of the velocity. We have uncertainty in velocity, and they want us to know uncertainty in position. And it's 1% of that speed. So we do have to multiply it by the decimal. 1% in decimal form is 0.01 times 5 times 10 to the 6. And I said 5.0 equals. That equals 5.0 times 10 to the 4 meters per second. Okay. So that's one part of the equation. And let me just put a dotted circle around it. Okay. We're going to plug that in. Well, I think we could plug that in right away. The uncertainty in the position equals, or times, the mass. The mass is 9.11 times 10 to the minus 31. And now we have the uncertainty in velocity. We had the percentage, and we converted it into a decimal and multiplied that speed by that uncertainty. Because it is 1% of the speed. That's the error or the uncertainty. And that is 5.0 times 10 to the 4. Greater than or equal to. And our final answer will discuss what to do with this greater than or equal to. But we're still plugging in numbers. 6.63 times 10 to the minus 34 over 4 pi. Okay. On my calculator, what would I do? On my calculator, I would take care of this term first. Let's do this together. 6.63 times 10 to the negative 34 divided by 4 divided by pi. Bring these terms over. So we're going to divide by 9.11 times 10 to the negative 31. And again, divide by 5 times 10 to the 4. Whoa. Let's get this into scientific notation so we have more digits to work with. There we go. That is delta x. Delta x equals, and actually, let's not lose the greater than or equal to symbol. I'm looking for my whiteout, and I can't find it. Oh, how about that? Greater than or equal to what? This number here. 1.16 times 10 to the minus 9 meters. How do you want to think about this number? That is the answer. But what does that mean? Okay, it's a very small number, but also this diameter is a very small number. So this is what I would expect in terms of your interpretation. The first thing is that 1.16 times 10 to the minus 9 meters is the minimum uncertainty. You could definitely be more uncertain, but this is as certain as one can get in terms of the location. Maybe you could even think of it as plus or minus 1.16 times 10 to the minus 9 meters. So that is the minimum uncertainty in the position of an electron. But look at the diameter. The diameter is smaller than the uncertainty. And what we want to say is that, let's take the ratio then. The uncertainty is, we take our number that we calculated for the uncertainty of delta x over the diameter, some dimension of the particle, equals. And this is 11.6. So what does that 11.6 mean? This means that the uncertainty in position is 11.6 times greater. That's very uncertain. When you have an object and the location of that object is has an error of 11 times that size of the object, then that comments on how uncertain one can be on that position. When you have what? When you have some certainty on the speed, okay, or at least this uncertainty in the speed. All right, so let me finish my thought. The uncertainty in position is 11.6 times greater than the atom diameter. Okay, and I apologize. I totally screwed up. That's not. We're still looking at the electron, and we want to know, right, the position and speed. Okay. But I totally messed up. That's the diameter of the atom that contains the electron. The electron itself is tiny, but the position of that electron within the atom, right, there's an uncertainty. That's the uncertainty. And that uncertainty is so much greater than the atom itself. So that speaks to how one can relate, right, the position of an electron in relation to the size of the atom. I know it's a little bit tricky. If I would suggest watching this video one more time or reading the textbook and how they approach it. But in terms of calculations, if you're given some certainty in the speed, you could definitely figure out the uncertainty in the position. Where do I have that? Certainty in the position. Once you have that uncertainty in the position, again, which is in meters, you can now relate that to the size of, in this case, the atom, where the electron should be found, right? It should be found within the atom. But the uncertainty in this case is much, much larger than the atom's size itself. Okay. In a future video, we are going to now try to locate or at least show where an electron can be found most likely within an atom. And you know that as orbitals. So we are going to get into something a little more concrete in future videos in this unit.